All right, thanks everybody for attending the E3SM All Hands Seminar. We are restarting the series and we'll have speakers regularly at this time every other week. And I am the new organizer along with Wu Yin and Jill. And this week we're happy to have Benjamin Wagman and Andrew Yarger from Sandia speaking about auto-tuning E3SM using a surrogate model for climatological spatial fields. Thank you, and I'll let you guys take it away.
Thanks, Mark. I'm Drew Yarger. I'm a postdoc at Sandia. I started in July of last year. And this work was originally started with Benjamin Wagman and Kenny Chowdhury, but I started once Kenny left Sandia. We're working on this with my postdoc advisor, Lindsay Shand, as well as Andy Salinger at Sandia National Labs. And we also want to thank Peter Caldwell for helpful input in this process. So we'll be presenting our auto-tuning approach and what we've been working on, but I'll start by handing it over to Ben.
Yeah, so the goal of auto-tuning is to use machine learning to expedite and formalize E3SM tuning. And like most Earth system models, E3SM is currently tuned by hand or by experts, and that's not going to change entirely. Just we're not going to change over completely to auto-tuning, but auto-tuning can help expedite the process. That is, find optimal parameters very quickly and formalize it to make it repeatable and make the rules very clear. So we have a four-step process here that we follow, our workflow, and our talk will kind of follow the same structure. So the first thing that we do is generate a perturbed parameter ensemble, that is E3SM simulations run with different values of tuning parameters. And then we build a surrogate model that maps from those input parameters to the spatial fields that the model outputs. And then using that surrogate model, we calibrate and optimize the parameters by basically trying to find the set of parameters that will produce output closest to observations. And then we take that set of parameters and run them in the actual E3SM model to make sure that it produces a good simulation. So the first step of this is to create the E3SM perturbed parameter ensemble. And the way that we're doing that is using a Sandia UQ tool called Dakota. Dakota's been around for a long time. Many of you have probably used it before. And the way this Dakota E3SM coupling works right now is that I create a YAML file that has the basic configuration settings for the ensemble that I want to run. That is, what parameters, what are the ranges, how many simulations. And Dakota reads that and does Latin hypercube sampling. So it chooses the values of the parameters within the bounds to fill out the space. And then Dakota calls the E3SM script create clone any number of times, as many simulations as I want to run. And then Dakota passes the parameter values into the name list for each simulation. And then I have additional scripts that go submit the simulations in bundles because that's more efficient, and post-processing scripts as well. And so the code for this is on the E3SM GitHub, and I think it's open, at least for people who are on the E3SM project. So using this workflow, we've created two perturbed parameter ensembles. The first one was with the NE4 version of E3SM v2, and that was just to basically get our tools set up and working right. And the simulation, all the results that we're going to present today are from the bolded row here, which is the v2 low resolution model running in the F2010 comp set. We perturbed 5 parameters and ran 250 simulations. Each simulation is 10 years long. I submitted the simulations in 100 node bundles where each simulation takes 10 nodes to run. And I ran these on Chrysalis. And there's a link to our Confluence page that explains more about the PPEs in detail, and the data is still on Chrysalis, and we've shared it with quite a few people and are happy to share it. So for the V2 results that we'll present today, we sampled these 5 parameters, which are common targets for hand or expert tuning. We sampled them with some bounds, some low and high bounds. And so that's the table on the left, and I won't read through the parameters in detail, but you probably recognize them if you've worked with E3SM or even CESM in the past. The spatial fields that we target are in the table on the right, and most of these fields are latitude by longitude fields, but 3 of them, the bottom 3 rows, are latitude by level. So they're zonal mean fields defined on 37 pressure levels. And the spatial resolution is there's a low resolution target and a high resolution target. And we did this because we weren't sure if we wanted our surrogate to try to predict the model output on the 1 degree grid, or whether we needed to coarsen the grid to reduce the noise in the spatial field. So we tried both. And then the product that we're targeting is listed on the rightmost column. So with that, Drew will tell you how we build the surrogate model.
So using the perturbed parameter ensemble, we'll try to try to define the relationship or estimate the relationship between your input parameters, those 5 parameters, as well as to the output fields that were on the right column of the last slide. So sort of in a visual representation of this process, on the right, in the green circles, we have our input parameters, the E3SM input parameters. On the very right, we have the output spatial fields. So our sort of process is to reduce these high dimensional spatial fields, 24 by 48 or 180 by 360, into a lower dimensional subspace using principal component analysis, or PCA. And then we'll try to fit what's called a polynomial chaos expansion from the input parameters to this latent space of principal components. So this is based off of Kenny Chowdhury's work at Sandia, and uses Python scikit-learn framework. So this is relatively flexible, and it's through the Python path through Tesseract, which a link is here. And early on, Kenny compared this approach of polynomial chaos expansion to a few different other approaches, and found it did similar or better compared to them. So we've continued to use this for our surrogate modeling. One thing that's nice about this is that the hyperparameters of the polynomial chaos expansion, including some sort of penalization for overfitting, so you're not just fitting noise, is chosen automatically by cross-validation. So it works well with Python scikit-learn framework. But this is a high-level overview of, how do we try to model the relationship between your input space, your E3SM input parameters, and the time averaged output spatial fields. So moving on to the next step in the process, we'll want to use our knowledge of this relationship as represented by the polynomial chaos expansion to optimize the parameters and try to find parameters that match well, that give output that match well with climate observations. So another high-level overview of this process, we'll try to minimize the root mean squared error, or RMSE, between the surrogate predicted fields and the observational data, so that those two things are close, by changing the input parameters and finding what we might call the optimal input parameters in some sense. So this optimization strategy allows for regularization terms that normalize the errors for different output fields, so that some of them don't sort of overpower the rest of them, and that you are able to have some balanced optimization of all of the fields simultaneously. This also allows a Bayesian formulation of the normalization, which we can use Markov chain Monte Carlo, MCMC, to visualize uncertainty in the parameters. I'll present a plot a bit later on that. But we're using the standard optimization software LVFGSB to do the optimization problem, to minimize the problem, so that the output fields under the optimized set of parameters are relatively close to the observational fields. All right, so to present sort of a more detailed version of the workflow, in the top row we have the E3SM input parameters. In the middle row are sort of the cycle that we presented earlier of our 4 steps in our workflow. And then in the bottom row is the E3SM time averaged spatial field output. So we have our perturbed parameter ensemble, different parameters X. We generate that to provide high dimensional output Y. To get a set of optimized parameters. And then this final step, which we'll go into next, is to validate these parameters in E3SM by feeding them back into E3SM and seeing if we actually get the expected results of matching better to observations. So yes, to dive into this validation a bit more, into the results, what we've done in this table is to compare the E3SM output with our Autotune parameter set and the version 2 control parameter set that was established. And we're computing area-weighted root mean squared error on either a 180 by 360 grid or a 180 by 37 grid, and then comparing them by evaluating the percentage change in the root mean squared error. So in this table, number represents and a red cell represents sort of worse root mean squared error for the auto-tuned parameter set, while negative number represents better or smaller root mean squared error under the auto-tuned parameter set. In general, we see improvement across the different variables and for the different seasons overall, although it's not uniform. But if we average it all up, we end up with about a 3.9% decrease in root mean squared error across variables and seasons. So one thing we're keeping in mind here is that the version 2 control parameter set likely included other considerations that we didn't consider here, like AMOC or El Nino or things related to a coupled model, but we're mainly just focusing on these 44, 11 times 4 output fields on the atmosphere model and seeing how well we can provide a proof of concept that the auto-tuning procedure works. So these are just numbers. We sort of want to dive a little bit deeper into the results. So I'll hand it off briefly back to Benjamin.
Yeah, so we also ran the E3SM diagnostics on every single one of the perturbed parameter ensemble members and in the runs. So the results Drew showed earlier were for the auto-tuned model, and that's the left column here in this figure. And this is from the E3SM diags intercomparison tool. And there are basically 2 takeaways from these plots. One, the auto-tuned model performs a little bit better than the V2 control in the standard E3SM diagnostics comparisons like root mean square error. And you see that in precipitation and in most of the fields that Drew showed, but I'm showing precipitation, winds at 850 hectopascal, and the relative humidity. The other takeaway from this is that there is there are large biases in the E3SM compared to observations, and the spatial patterns of those biases are the same for the auto-tuned model as the control. And that's because some of these biases are structural, and even if we perturb all the parameters, we would never be able to fix them. And also because we're only sampling 5 parameters, and the model has more uncertain parameters, and potentially we could do better if we sampled more parameters. But there's a tension between sampling more parameters and running a reasonably sized PPE and generating an accurate surrogate model. And one last point from this is that I included some MERA2 results to show that even though we tuned the optimization to area interim relative humidity, the improvements even relative to MERA2, it still improves relative to MERA2, and this is the case for most of the fields, that the improvement is not specific to the product.
So with the fact that Ben just mentioned that there are similar biases between the control and auto-tune parameter set, we were sort of interested in getting an idea of how well could we do? Could we expect to do much better than we did with the auto-tune parameter set? So I know a number of climate scientists looks at things like Taylor diagrams. So this is the Taylor diagram for one season for March, April, May. On the left, we have the 11 output fields with the version 2 control and the auto-tuned points, with normalized standard deviation on the x-axis, and then correlation between observational and E3SM output sort of on the angular axis, with points closer to this point on the x-axis of 1 being generally matching the observations a bit better. So we can see that the auto-tuned version of version 2 is generally a little bit closer to this point, a little bit of improvement in results. And then on the right side, what we've done is to zoom in to this area, and also in the background plot points each representing the 250 simulation runs. These points are lighter and smaller, so they don't overpower the auto-tuned and version 2 control points. But this gives us an idea of what really the perturb parameter ensemble gave us. For example, for U200, we see that the auto-tuned parameter set seems to do better than nearly all of the 250 simulation runs, so we wouldn't expect to do much better. But for some of the other variables, like the pressure at sea level, there are members of the 250 perturb parameter ensemble that are better than our auto-tuned parameter set. So maybe we could improve on this variable more if we give more weight on that in the optimization problem. This also gives us sort of an idea of what our perturb parameter ensemble allows us to deal with. For example, for the temperature variables, temperature and the temperature at reference height, there's not a lot of variability. So this just tells us that we can provide some improvement, but we wouldn't really expect to provide too much improvement there. So as I discussed earlier, another visualization we can look at is sort of a distribution of the uncertainty around our optimized parameters. So on the left, I've plotted the individual parameter bounds, and sort of the action of what's happening in this graph is sort of saying, oh, this is where we think the parameters give output that matches the observations well, based on the optimization problem you provided. So for example, we see that the sort of our idea of what are good parameters are relatively narrow in terms of what we originally searched for the parameter bounds. So we're wondering if we're missing some sorts of uncertainty in whether we can provide more uncertainty in these parameter bounds. We're not sure if we're taking into account everything. So these are relatively preliminary results. But one thing we have an eye on for the future is if we look at the right plot, we're zooming in again, and we can see some sort of bimodality in some of the distributions. For example, for ZM conv tau, there's a parameter set near 3200 where we think it'll fit observations well, and there's also a set near closer to 4000. So this could potentially be a way to look at these plots and say, oh, maybe we can have two candidate parameter selections and see how they differ and how they compare instead of just a single optimized set. All right, so these are our results. In general, we think of this as sort of a proof of concept on the version 2 atmosphere model. We have a flexible workflow for the automated tuning. It uses a surrogate model that tries to balance 44 different high-dimensional E3SM climatological fields based on different variables in different seasons. The surrogate function is independent of the choice of loss function, the optimization function. So you can potentially choose to, have some expert input into your optimization function to weight different variables or different seasons more or less. And we found that our optimized version 2 of E3SM reduces the root mean squared error by about 3.9% on average compared to the version 2 control. And we can try to provide a distribution of uncertainty around the optimized tuning parameters. So as we move forward, we're definitely thinking about how we can be useful for version 3 of E3SM, and I'll hand it back off to Benj to talk about our preliminary plans there.
Yeah, so we're starting to work with the V3 candidate model with an eye towards applying this to the auto-tuning to V3 as fast as we can. For that next ensemble, which is going to be run this month and next month, we've selected 8 tuning parameters, so we're targeting 8 instead of 5. We still think we can get away with about the same number of simulations because our results showed that we probably didn't need all of the simulations that we ran for V2. So we're targeting 200 to 300 10-year simulations. We're also targeting 1-year SST plus 4K simulations so that we can calculate the climate sensitivity and cloud feedback in each of these ensemble members. The simulations will probably be run on Chrysalis or Compi. For V3, there'll be input where the analysts can essentially provide overriding field weighting. And so our goals for V3 are to provide the optimal set of parameters in the F2010 configuration to assist E3SM in hand tuning those parameters. And we can also provide this distribution of tuning parameters. We're hoping to find some really high performing models that have different ECS values. And potentially adapt this tool to running E3SM v3 in different configurations outside of F2010. And this slide just has links to some of the tools that we've developed and to our Confluence page. So I encourage you to come take a look and provide comments. So thank you.
All right, thank you. And right on time too.